All right. Any questions before we start today? Questions? That's not the point. So this morning I did the really fun thing. I got to campus and then I realized I didn't have my computer. Yeah. And so I had to drive an hour back to my house and then an hour back. And so I decided to include this one here. This is a really important quote from Charles Darwin. Does anyone know this one? Okay. But I am very poorly today and very stupid and hate everybody and everything. So that's this is the mood. Okay. But the cool thing is that this person here, this is a homework solution, which you'll see in the peer grading. And I actually liked this video before I saw this. I thought it was really cool. What they do is they bring this little jug of water into a what are those things? Skydiving tunnel. And the water like floats around with you. Wind tunnel. Let's see if it'll run. You gotta run.
One of the coolest things in the wind tunnel is to see water floating. Poured from a jug, it quickly...
Okay. So here you can see the effects of pouring water in a wind tunnel. Now they can stand because the force of the water being lifted is much smaller than the force necessary to lift a human. Whereas if you dropped water in the same speed wind necessary to lift a human, all that water goes. You can just tune correct parameters for those drops. You can pour it out, and it looks like it's floating in microgravity. And in fact, water droplets don't make this teardrop shape, as you're about to see. They look like, ooh, weird fucking boys. Question? Okay. And as you see here, this thing breaks apart these little droplets. If you have a droplet that's too big, it's falling down. The entire shape deforms until the droplets shape themselves comes to the optimum size, right? Or fully evaporates, depending on how hot it is. Okay. Oh, and my watch time. This is a really good day. Just like 10 for 10. Okay. So we were talking about this adiabatic lapse rate. Can you explain this to me? You were like, yeah. No means yeah. Someone in the background? What's adiabatic mean? This. No heat going in or out of the system. That's right. Remember the adiabats, right? There's a bat. I put a bat on the thing for you to remember adiabats. Come on, you have to use these brain tricks to remember what the hell I'm saying. There's Greek words. Word adiabatic means not allowing something to pass. When you talk about adiabatic in the context of thermodynamics, it's not allowing heat to pass into the system or out of it, obviously. So what we're talking about here is an adiabatic lapse rate. So we're talking about taking a parcel of fluid and raising it up or putting it down, however you want to do it. This is in hydrostatic equilibrium, right? By definition, we're still talking about fluid statics. This is still chapter 1. And what we're doing is we're asking what will happen to that parcel of fluid afterwards, after you make that perturbation. Okay. So down here, how's the density compared to right here? How's the density here compared to here?
It's more dense.
More dense going up? Raise your hand for more dense going up. Raise your hand for less dense going up. Raise your hand for the same dense going up. Raise your hand for what? Okay, let's ask that question again. At the ground, so this is height. That's a kilometer. As you go up in altitude, how does the density change while temperature is decreasing? Anyone ever been to the top of a mountain? What happens? It's hard to breathe, but also cold. So both of these happen at the same time. So intuitively, when you think at the ground, you say, well, when it's cold, that means it's more dense, right? You say, oh, all of that gas is going to contract. Well, you've baked in an assumption. Because you've baked in an assumption about the pressure. And that's not necessarily valid here. So you go up in altitude, the pressure goes down. Why does the pressure go down as you go up in altitude?
Less gravity.
No, gravity is the same. Yeah. That's particles where? What causes the pressure? I'm going to say this again. We said it last time. Really, really important here. What causes the pressure in the fluid? The column above you. So by definition, the pressure is going down as you go up.
That's true.
Okay. Okay.
How it works in like water.
Well, yeah, it's exactly how water and the fluids are the same here. The only thing, and we're going to see so many similarities between air and water. The major differences that you're going to see, and as we talk about some of the experiments when we get into kinematics today, it's just changing that viscosity. It's changing the inertia and it's changing the viscosity. And the problems will look very similar because all you have to do when you relate them is change flow and they look the same. Okay? You're excited, right? Okay, so let's understand this again. You start at the bottom, you go up. Temperatures go down. Densities down. Pressures down. Oh, shit. Okay, good. So you go all the way up here. I take a parcel from the bottom. I bring it up. Is it heavier or lighter? It's. I take a parcel from the bottom. Bring it up. Is it heavier or lighter? Yeah, you're heavier, lighter, same. So someone has to make an argument for their decision. Yeah.
I think it's going to be lighter because thinking of like a Dorito bag, taking up all the area inside the Dorito bag is going to stay out.
Okay.
First. So I'm thinking maybe there's a difference in pressure.
There certainly is a difference in pressure, but by your reasoning, that gas would be more or less dense. What causes the bag to burst?
It would be more, yeah.
Pressure from the interior does what? It's more gas inside the bag than outside the bag. Therefore, the density is higher.
Okay.
So good example, but backwards on the interpretation. Right? So as we go up, exactly right, take that Dorito bag. It's now more dense than the rest of it. And so what does it want to do? Thank you. Assume that, of course, it doesn't have an actual coating, right? Because it would pop and then fuse really quickly. But if we take a parcel, large parcel, bring it up, it's heavy, and it sinks. Make sense? Okay, except for, so you're in this region, you bring it up, it's stable, it sinks. What happens in this region? Very stable in this inversion. What the heck? This is weird. So it's like hotter up here, and it's colder down here. So hot's on top of cold. Now I take a parcel of this gas, and I bring it up. Which one is more dense? Bottom one is still more dense. Because here the temperature is higher.
The temperature higher because it's like closer to the sun or something?
It can be for a number of reasons. You can have a thermal inversion just from heating, like coming off of the surface, being absorbed at, say, a cloud deck or something right here. This is an imaginary or an idealized example. Okay. So here you can imagine a world in which you have three variables to play with. You have the density, the pressure, and the temperature. So what I've done here is I'm not telling you what the pressure and I'm not telling you what the density is here. But I am telling you that just from temperature, from the fact that it's an ideal gas, and you have a slope like that, This part here is less dense than this part is here. But that's the opposite of what you just said. No, it's the same. Now there's a weird one. We don't have it on here, but if you have it steeper, or sorry, more shallow, if the temperature gradient goes like this, like that, and you change temperatures very quickly compared to what the adiabatic lapse rate is, then you get instability. And we can see that because if we take a fluid out here that's really hot, and we bring it up towards a region where the rest of the fluid is much cooler, then the hot air continues to rise. Even though you might intuitively think, well, the density, that's fine. Density makes it go down, but it's a dense hot gas. Make sense?
So if you pull it through really fast, it'll start having instability?
Yes, right. So if you pull something dense hot gas, don't let it exchange with the environment, right? Don't let heat escape. You pull it up to a temperature, an altitude at which the surrounding gas is a totally different temperature. It'll say, I'm going up, all the way up. Right? Does that happen indefinitely?
Wouldn't the illusion keep going up little by little?
Yeah, so in a real situation, it certainly would. And in fact, what we're talking about here, look at it, look at the scale. That's 2 kilometers. How big is the atmosphere on Earth? What's the unit? Is it feet? Is it apples?
Oh.
Atmospheres, that's a cheeky one. Okay, so kilometers is correct. You said tens of kilometers? Okay, that's bigger than this, which is good. It's on the order of 200 kilometers. Okay, so depending on where you want to describe the homopause versus the exobase, which is a great discussion for another class. So we're really at the bottom. We're at the part that we breathe. And of course, the types of dynamics that we talk about here are not going to be valid all the way up. Make sense? Okay, no more questions about this, or we can still have questions. That's okay. Okay, so let's write some stuff down, because we love solving problems, right? So many shakes of the head. Okay, hold on. First thing we're going to do here. All right. So if I write something like this, let's write some things down. Let's write this. What do these pieces mean?
Density.
Yeah, density's here and gravity's here. And what's on the left-hand side?
Change in pressure or height.
Change in pressure or height. So how would you interpret this word? This is all English, right? The pressure changes as you change the height. How does it change? Negatively. So as you increase Z, P goes down, and by this amount. Okay. Which of these depends on Z? Density certainly does, right? What about G? Not really. So if you want to think about it in the context of G, right? So how big is the Earth? Let's go back one. Order of magnitude. How many kilometers? The Earth itself.
The diameter?
Yeah. Yeah, it's like 6,000. Okay, so 1 kilometer, adding to that, is that a big change? No. And in fact, the gravity near the surface changes very little. Of course, if you want to have a very, sophisticated measurement, you can go up to the top of the mountain, you'll see that it will change, of course. But for our cases, let's pretend that G is a constant. Okay? But this does depend on Z. So is this solvable? Yeah.
What did you say? Oh, it's like the height changes, the density. What did you say about the equation? What does it like mean, like the sentence?
Yeah, someone explain that, please. Someone who hasn't talked today.
What is the equation? What is the increase?
Sentence.
Z,
As you increase Z,
D decrease.
P
By
decreases.
That amount, negative rho times.
So we know that because this piece here tells us that when Z goes up, this value goes down. That's the rate of change. It's a negative slope. And then this thing that we're talking about changing is P, the pressure. Okay, so how do I relate this thing to this thing? We're going to assume that we're starting right here. Okay. Anything we can use? Not necessarily. Yes, you're on the right track. There's something I want to use right before that. Something that relates just maybe this thing to this thing.
The ratio, the pressure over.
That's what he said.
Oh, okay. Oh, what you're saying.
The step before that.
E equals rho times R.
E equals rho RT.
Yeah.
Would that relate the two?
Yeah.
It does, in fact, relate the two. Good. Okay, so now let's make a little switcheroo. Okay, how would I write this in terms of P? Yeah.
Do we?
Oh, you want
I have a differential on the right hand, left hand side,
Integrate?
and I have something wrong. No, we're not integrating. I want to relate these. I want to get rid of this.
Oh, move the D's into the other. So,
Divide by RT, correct?
okay.
Oh. Shit. Get the wrong conclusion.
So sorry. So sorry. Still negative.
Very good. Okay. So now how do you solve this? So don't say it. Write it down. What do you think? For P, yeah. Yeah. I want you to solve for P. Is this solvable for P? Any issues? Let me know if you have a problem. Let me know if you need to make an assumption.
Temperature constant.
Ah, yes, this would have to be an isothermal system to solve easily. So let's assume T is constant. And the only things that are changing are pressure and density. You have it? Everyone's heads are down, so I can't tell if they fell asleep. Got the best part of the lecture, and everyone was like, yeah. You got it? What are you lost on?
Do we do the integral?
You could do the integral. You should recognize this differential equation. Can I show you a different version? Okay. What is this? What is that? Yeah.
How did you get the dp divided by dc equals negative d over rtg? Where did that?
Which part?
The top right.
This one?
The
So
whole thing.
we started with this. Okay, I made that statement. Okay, and then I replace this with the ideal gas law. And I get this. Make sense?
And one then. Oh.
So what's this? What's the solution of that?
That's like, hang on. Let me think about it.
We see.
What? E to something. So what's the fun thing about the derivative of e to something?
It's still e to something.
It's e to the same thing.
Yeah.
Okay, e to the same thing. That's a fun one, right? That's one of our favorites. You see it all the time in nature. You take a derivative of e to the x, you get e to the x. Okay, what about this one? Okay, so you put that back in there, and where does the b go? Oh, b goes to the front. Oh, what does that look like?
That looks like what we have.
Okay, so we want to solve these by inspection. You look at it, you're like, I recognize that. That's my good old friend, the exponential. Okay. So how do I write this? What's the solution to p as a function of z?
E to the negative g over e.
G?
Yeah, g over, that's what I got, sorry.
Well, I don't know. Tell me if I'm right or wrong.
I think it's
Little g over RC.
G?
yeah, over, yeah.
RT
Z? Okay, good. Put a little z in
I
there.
put K instead. I misread my own writing.
Uh-huh,
It was
okay.
R.
Okay.
Yeah. So sorry.
Plus a constant.
Plus it comes.
And what would that constant be?
10. No, it's just
The initial pressure. So when z is equal to 0, what do you get? Put it in there. 1. But that's not very meaningful. Okay. Well, P is equal to E. So in fact, I need another constant right here, right? That's where the P naught goes. Right? Okay. So that's just what I'm talking about here. We describe this thing, RT over G. That's called the scale height. That's a distance. In fact, if you look at the exponential, Z exponential has to be dimensionless. So if the distance is 1 kilometer, you have to divide it by something that's also in units of a kilometer, because that way the kilometers cancel and you get a number. Yeah.
What could say it's E.
What?
Because it-
The reason that you're interrupting for that?
Yeah, sorry.
Okay. So what we want to think about here is the scale height itself tells us how quickly the atmosphere is decreasing in density. Okay. And in particular, we know what E folding is, right? So this is how much it goes down by a factor of E. So for every multiple in the exponential, you've reduced it by a factor of E. That's what the definition of exponential is. 1 over E times 1 over E, 1 over E, and 1 over E. Right? People familiar with that? E to the minus 2 is equal to 1 over E times 1 over E. Correct? Correct? Okay. How much is E? I'll go with 3. The astrophysicist, so we just round everything up. 3. And so what is 2 E foldings? 1 over 9, correct. So if I go up 2 scale heights, how much has the pressure dropped? By a factor of 9. Okay. So it's hard to breathe. What's the scale height on Earth? Yeah, 5 or 7 kilometers, depending on where you are. Okay. Cool. Yeah.
So this energy function is just like how something like directly to the atmosphere.
Yeah. Yep. In an isothermal gas. Yeah. Not everywhere, but in these very specific cases. Yeah, when we make this spherical cow, the assumptions of our hydrostatic equilibrium, we assume isothermal, then you can make this statement. Now, is this a very good starting point? Yes. Is it good everywhere? No. Yeah.
Still could be like PZ in front of them.
Yeah.
Why is it P not in front, not the negative G over RT? Why does that not come in front?
Because I haven't done the differential. Take this and plug it into this differential. But take the derivative of this. Yeah, take the derivative of this and see if you get that. In fact, you're guaranteed to get it because that's the solution. Right? I didn't make this up. I'm not that smart.
So we're supposed to know that from the exponential force.
So if you have this here,
yeah,
you can take, how would you solve this? Well, you'd have to, of course, it's a little annoying. You have to do the integral, right? And in doing the integral, you're going to use some logarithms in order to figure it all out. And that's where your E comes from. But if you recognize this form for the differential, anytime you take a derivative of something and you get something times that thing back, it's an exponential. If you, for example, looked at the simple harmonic motion and you said to yourself, wait, I take two derivatives of it and I get something back that looks exactly like it times a constant, you'll notice, oh, that's also an exponential. But because I have two derivatives, it now has to be an exponential with an I in it. And an exponential with an I in it is a sine and a cosine. Does that make sense? Okay. We can have a whole exponential discussion in the student help sessions. Okay. I promise. They'll be so natural to you by the time that you're done with this. Maybe. We'll find out. Okay. Let's go into the next question. So we're going to skip all of 2. Ready? We're going to go right into 3. Shit, this takes a long time. That's 2 slides. Okay. Let's talk about kinematics. What are kinematics? Okay, specifically?
Motion without talking about forces.
Without talking about this. So we wanted to find the motion of the fluid without the reference to the cause of the motion, because we haven't defined Newton's laws, we haven't defined conservation of mass, conservation of energy, anything like that. We'll do that in chapter 4. So this chapter is short. It's annoying. Chapter 3.6 is like the dumbest first sentence I've ever read, because it's like, so like, why would you even do that to someone? But we're going to basically go through some of the tools that we're going to need before we get into what's fun about fluids. Best part about fluids is watching them move. They're like so interesting. Okay. So we need to see a couple different things here. We got to think about the places where we see symmetry. Okay. We have to think about what it means for things to be steady and unsteady, and how we transport material elements in the fluid, how we transport properties of the fluid, and how it changes with respect to reference frame. Okay. When I throw a ball to Giselle in the back, regardless of whether I'm in this reference frame or I'm in a moving reference frame, laws of motion are pretty much the same. There's just a little translation, right? And I'm going to show you fluids make it off like that. Okay. So first question, what's steady flow mean? When the flow doesn't depend on or doesn't change? Doesn't change. It's very close there, right? Because the flow itself can be a function of time, but that time is constant. See? Flow field not changing with time. The derivatives of it with respect to time, 0. So it is moving, but it's not changing. You see how that's different? No. Okay, so flow is what? U, right? And if you had a giant pool like this, you also had very nice pictures, like your water bottle sitting there doing nothing. There, the flow is steady, that's true, but also 0. The flow itself is 0 and it's a constant. Whereas, if I have a flow through a tube, right? Let's say I'm putting flow through a tube, and the same amount of fluid is coming out of one side as going in the other. And it's say 30 apples of water per second. Arbitrary unit, right? It's always the same, always the same. Is that steady or unsteady flow?
That's
Steady. Right? Now let's say I put my thumb over it and then off and then on and then off and I'm spraying you all with the hose. Steady or unsteady flow? Unsteady flow. Does that make sense? Okay, so you can have something moving, but it's not changing. Okay. All right. So now we need to have some fun. Write these down. So I'm going to explain what these are. And you're going to tell me, without looking right at your book, to find the answer. Because it's right there. You could do that. We're not going to do that. We're going to try to identify the sources of symmetry. Which direction is a symmetry? And I'll do the top one for you. Okay? Here I have flow coming in from the right. From the left. Okay? And then it piles up. And then it becomes rarefied. And then it piles up. And then it becomes rarefied. And I want you to tell me in which direction X, Y, Z is the variation. Just write it down.
variation.
Variation. Where is it? How is it varying? And how is it symmetrical? Okay, so this would be the R direction, and this would be the Z direction. R, Z. No, write it down.
Oh.
This not steady or not steady?
Those are the same questions.
Okay, what do you guys think? What's the question?
I'm asking you, what is the symmetry in each of the examples on the left? Which direction is the symmetry? Is it in R? Is it in Z? Is it in phi? Is it a combination of any of those? Is it none of those? That's right. We've already done A, try B. We've already done B, try C. We've already tried C and D, and raise your hand. What's that? That would be phi. Phi, or theta, or whatever you want to call it.
What is final?
Yeah. Maybe.
I was like,
Phi is the, so if you imagine this is a tube, this is the angle around the tube, and you're looking through a cross section.
but if you're asking if it's symmetrical according to is it same sun?
Of course, these are in 2D, so phi is implicit here, right?
Okay.
Okay, let's start with the top one. A. Where is it symmetric? It's symmetric in R. So there's no change in the radial direction. There's only changes in Z. Okay, that one was easy, right? Okay. What about B? Phi? Phi is not present, but yeah. You're right that these are both phi. Anything else?
For B, they both the same in R and Z?
Is it the same in R and Z?
Or are they both?
Yeah.
Symmetrical, it's like if you folded it, you would say on both, or is it just not change?
Oh, wonderful question. What is symmetry?
It's like a reflection.
So people think of symmetry as it has to be the same if you fold it like origami. That's not necessarily the case. So what I mean by that is when you think about the symmetry in a problem, you're really looking for the places where different stuff is happening. Where are your independent variables? Because if you imagine, for example, that something is constant in 3 dimensions, then you would say it's uniform in all those dimensions, right? So when we're talking about fluids here, maybe the word symmetry is not great. Maybe we don't like that for fluids, but we're not talking about taking this flow and folding it back on itself, because that introduces a mirror that is not there. This is a rotation of the fluid that is not present. Instead, we say there's translational symmetry, that a slice here looks the same as a slice here, whereas a slice here does not look the same as a slice here, despite moving in Z. Does that make sense? And of course, there's phi symmetry, because that's how we designed it. But if
I'm sorry, but then for B, would it have both translational or
right, so let's think about this. Let's imagine that this is the line here. Okay, as I move upwards, is it symmetrical? No.
Oh, okay.
Right, because it's getting shorter, because flow is going down towards the edge. So there lacks symmetry in the radial direction. But there is symmetry along the flow direction. Does that make sense? So this tells us that we can solve this problem by only considering a single point in the flow. Right? All I have to do is look at this location Z, and that will tell me the locations all along the Z direction. Whereas here, I only had to solve at one point R, and it would tell me all of the directions in R. What about this one? Not symmetrical in good?
And Z.
And Z. Okay, so this one's really fucked up, right? So this one here, not symmetrical in R or Z. It's changing this way. Changing this way. What about this one? It's symmetrical in R?
Yeah. Oh, but
Oh, it's getting narrow.
It's getting narrow. Okay, so we have to be really careful here, okay? So it's just a warning sign. And you can, of course, look in your own book. They have really fun names for them, for axisymmetrical. So, for example, that's the rotation that we're talking about here, that we're just ignoring the two-dimensional page. Okay? So we're going to talk about fluid flow in a couple different ways. We're going to talk about the particle versus the field description. And we're going to come back to this picture in a little bit, but I want to show you some examples here. So here on the top, you have a cylinder. You can think about this like a rock in the stream. And you're looking down the stream, okay? And a little leaf is going by, and the leaf does not go through the rock, right? It goes around the rock. Everyone have experience with that? Okay. So we watch the path of the leaf as it moves. Okay? And this would be the Lagrangian motion. The Lagrangian motion follows the particles themselves. Okay? As opposed to Eulerian motion, which describes the flow to a fixed point. What would that look like? Well, that would mean I choose a point like this here, and I'd let stuff go through it. And I'd ask, how do you change? Okay? A lot of the stuff we're going to see here is going to have two flavors. You already saw that we have a form up here. We can differentiate, and you can integrate. So when we look at the equations of motion, we're going to have both an integral form and a differential form. And I prefer the differential form because it's easier to code with. But we want to understand the integral form first. And this one here, the question is, which is better? The Lagrangian motion or the Eulerian motion? That's what you use it for? Okay, sure. Okay, so you think if this one is going to lose some detail? Is it? Okay. Who here is Team Lagrange? And who's Team Euler? Who doesn't care?
Whichever one's easier to solve.
Whichever one's easier. Okay, so they both are going to be really interesting. Let's have a look at this here. So I always pointed at that, and it's my computer. I do this in my house too. I point at the screen, and there's nothing there. It's a projector. Okay, so let's think about this. 3.1, and this is just math, so it doesn't really matter, right? We don't like math. We like physics in this class. 3.1 is this fun definition here. Fuck, I need more space. Okay. And it defines U, oh god, as dRdt, where R is a function of t, and the initial conditions are not and t naught. Okay, and then A defined as d squared. R does the same things. R naught, t naught, d squared. Am I missing anything? It's a small detail. The arrow on top, which means they're vector quantities, right? Okay, because I can't draw bold. At least not as far as I know. Anything else I'm missing? Any of the arrows? The R naught, of course, has to be an arrow as well. Okay. So T is a scalar property and the position is not, right? And this is the description. Oh, it's right there. Copied off the board. Okay, so what does it mean? It means I started at some location and I want to watch the fluid evolve. So I'm following along some flow. You're going to notice in fluids, this parameter that we're talking about, it can be anything. We could be describing the heat flow. We could be talking about the salinity. But what's happening is that it's moving because the fluid itself is moving, right? So we're going to have to always talk about it with respect to the flow, U. Not moving, it's coming. Then you can just do chapter 1 on it. So you can look at any point here. This is parameterized by this curve. Okay, that doesn't necessarily have some beautiful solution for it. Most flows are weird and annoying. Okay. You take any property of that, you apply the chain rule. Let's say you take something like a really fun part. ddt or property F. Okay, this property F is going to depend on R. It's going to depend on P, on R naught, and T naught. Okay. We can do some fun stuff with this, but essentially what you're going to end up with is something that looks a lot like this. That. Either part of those. Yeah. Yes, there's a gradient. Very good. So this is the gradient of F. What does the gradient tell you? What's that? What does it mean?
Rate of change in space.
Rate of change in space, so it's telling you, yes, that's true, but what does it mean? When is it 0? When it's flat, it's uniform, right? So it's telling you about the non-uniformities in the flow, right? Spatial non-uniformities in the flow, okay? What's this piece do? Right, those are the show finding that. What's the word for that? Something's changing over time in the terms of our fluid. Unsteady. So this would be the unsteady term. If the fluid is not changing with time, this thing is 0. By definition, ddt of something that's not changing with time must be 0. So we call this the unsteady part. Okay. And this whole thing gets its own name. This is something you have never seen before. Okay, so I did not fuck that up. That is actually what it looks like. You get capital D's. And this is called the total derivative. Okay. So we said that there's a gradient there. What does that dot U fucking mean? That's crazy, bro.
Gradient in the direction of U.
Gradient in the direction of U. Okay, so usually when I try to look at math, if I'm trying to understand a term that doesn't make any sense to me, I want to think about it in the context of how do I break this thing and does it tell me anything about it? So this is in the direction of the flow. Okay. When is this product 0? We already gave one example in the gradient of a uniform object, right? That would be 0. Okay, so nothing is changing. That's a boring one. What's another one?
They're
The perpendicular. Okay, so wait, let's go back a second here. Let's go back to. All right, so we have a spatially varying fluid property in the direction of flow. Okay, so let's imagine that this is not showing you the flow, but maybe the density. Okay, and let's say the flow was that way, and the density decreased as you went out. But it's uniform along the flow. So low density up here, high density in here, but this high dense material is pushing on high dense material to the right. So the density doesn't change along the center line, and it just varies as you go up. So that, since they're perpendicular to one another, is not going to bring any flow along. All the flow is just staying where it normally would. You move to the right with the fluid, it would look like it's staying still. It doesn't look like it's going to change. What's that process called? A weird word that you maybe have never heard before. Yeah. The process of bringing something along in the flow is back. Advection. What a fun word. Don't we love that word? Advection. What does advection mean?
It's not convection.
It's not convection. Very good. It's that term right there. That is advection. So this is the process of bringing something in the flow. Okay? So the fluid is moving, and it will drag material properties with the fluid. That can be heat. That can be density. Okay? But when you do dot that fluid property, gradient that fluid property dot U, that's advecting it through the direction that we're interested in. Okay, so we did 2 examples. We did the gradient can be 0. That would make it 0. The dot products can be misaligned. Anything else? That's the dumb one. Fluid's not moving, you can't affect anything. Does that make sense? Okay. Oh, I don't even. All right. Go on. Oops. So let's define some more fun things. These are more tools we'll need. Stream, path, and streak lines. All those words have the word line after them. Streamline. You heard of a streamline before? What do you think streamline means? Like in your day-to-day life?
To make more efficient.
Yeah, car go from, right? Streamline, right? What about path line? Ever heard that before in your day-to-day? No, of course not. What about street line? Group of people running through campus? No. Right? Okay. So we have some definitions here. And they're going to seem trivial. They're going to seem useless. But they will be meaningful. Okay? A streamline is defined as the tangent curve to the fluid velocity at all points at an instant. Okay. All points at an instant. Nope. They are a line. Okay, so let's have a look. This is X, and this is Y. I might have a fluid flow, right? Why did I draw with all those arrows? And U is what kind of property? It's a vector property, right? Remember that every location in the fluid in XY space, it has a direction and a magnitude. So if I drew the super good, those might even be different length, right? I'm not that good a drawer. So now let's imagine I am a super good drawer. How would the streamline be on this at a point T? So yeah, so it'd be tangent. Okay. Instantaneous. Okay. So if the flow doesn't move, kind of looks like a human head.
Nice to see you.
Oh wow. Yikes. Okay. So what is a path line? A path line is where a single fluid parcel has been and will go. So let's imagine now for a moment that I start over here on my own shoulder. Okay. And I go boop, 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 over my head, boop, boop, all the way down, and on my arm that's outstretched. Okay. Okay, that's the path line. Path line, streamline, coincide. Very cool. Streak line is a curve that connects all fluid particles that will pass through a fixed point in space. So not only will that little drop go all the way over, all the other ones will too, right? But why the predefinition?
Would it be different if the flow is changing over time?
Exactly. So this is only the case for steady flow. And steady flow. We're going to start with steady flow, but it's much better to be unsteady, right? Everyone likes when you're sort of arranged, right? Okay, so let's look at this. Here's the streamline. Boring picture, not as good as my picture. Okay. So here's the picture. At this exact point, you have this tangent to the flow. Here's the flow direction. It's going to change a second later. Streamline doesn't know that. It's just living its best life, right? Okay, here's a weird one. Okay. Be hard to understand. Here we have a flow at a time t that is varying up and down, sinusoidally. Okay? The path line, the streak line, and the streamline are all tangent to one another. So let's go back one step. Streamline is defined as the instantaneous tangent in the direction of the velocity. So let's look through a point right here, this dot right here. So that means that its flow must be in which direction at this point? Yeah, it's that way, up and to the right, right? Okay, what is a path line again? Yeah, it's where a parcel has been and will go. So this piece of fluid, this baby boy here, came from right here. And before that, over here, and then here. And he's just making little circle boys. Now, okay, wait, this is going to mess everyone up. What's the bottom one doing? Streak line means what? Okay. So does that confuse anyone?
Yeah.
Yeah, that's pretty confusing. So streak lines there on the bottom define all of the points, but the other guy's going up. What the fuck? Well, the path line says that this fluid parcel is only ever going to go up and only ever going to come down. So what's changing on the right-hand side? Yeah, let's redefine the streak line. What is a streak line? Isabel, do you want to say it again?
The curve that connects all fluid particles that will pass through a fixed point.
Interesting. Fixed point. That was here, wasn't it? Mm-hmm. So all of the fluid particles that will pass through here come from here. But the particle that's currently there, the only time that it ever spends there is here. And from then on, will go up and live this life. Why? Because the fluid is unsteady. The direction of the velocity is going to continually change. So at this exact moment, this point here is the life for that little tiny fluid parcel. Whereas it will continue on in this direction in time, versus this tells you all of the pieces that will run through this piece of space. And this tells you the tangent of the velocity at a specific time or a specific point. Do you see how all three of these definitions are now different? So which one tells you only about space, a specific point? A streak line. A streak line tells you about all of the particles that will pass through a specific location. Okay, your flow is up here, and I want to know who's going to make their way through that. Whereas a path line tells you
with a certain parcel of fluid will be going.
Right. So if I could somehow like radio tag group of air, where will that single group of air go? Right. Versus a streamline tells you at a specific time what the flow looks like. So you can take pictures of the flow. Click, 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 click. They will show you the streamline. Right? Okay. Anyone confused?
Yeah.
Good. Everyone should be confused. These are not intuitive feelings. And in fact, that's why we have fun videos. Oh, yay! Okay, so this is an old ass video. And when I mean old, I mean old. Older than me. Black and white. I know, it's hard to believe anything's older than me. Okay, so what you have here is flow visualization. And I don't remember when this is. Hello. Why not go? Okay. So this is a video. It's about 30 minutes long. I'll send it to you, or it's on YouTube or whatever, when you can look at these slides. We're not going to watch the whole thing, but this is what I learned on. I think it's from 63. And they're just not making them like they used to. Okay. So what we're looking at here, we're going to look at flow visual. Oh, God. The compression artifacts are awful. Okay. So when we get to the point that I actually care about, you can just look at this up there. They're going to show you different ways of doing this. But essentially the way that you make this flow work, this is in liquid. And what you do is you get a little piece of metal. And in that metal, You drill little holes, or you put charge on it and you get water to get the bubbles out of it, right? And so you can visualize flow this way. You can do this gas. That's a gas version. But see these gas rolling up? So you can visualize it by injecting gas or dye. We're going to inject bubbles here, and we're going to look at the flow. In particular, we're going to look at the flow of streamlines, streak lines, and path lines. Okay? They also talk about timelines when you watch this video. Don't listen to that word. It's a bad word. We're not going to use it in this class. Okay? Okay. Cool shit, right? So I wanted to get a wet lab for this, and they're so expensive. Like just doing all the water demos, you have to have like so much equipment, so I wasn't allowed to. Okay, so let's go. Let's get down. Hold on. Excuse me. Oh God. Okay. Here we go. This better work. All right, so here's the bubbles.
In order to interpret flow pictures, we need to be quite clear about 4 concepts. These relate the pictures to the kinematic description of the flow field. The first concept is the path line. A path line is the trajectory or path of a given fluid element. Here we mark a small element with bubbles so that we can follow its path. If we took a time exposure, we would make the entire path visible. Instead, we superpose a path line, and you can check for yourself that each of these squares follows it.
Right? So what does that mean about the flow? It's what? It's a steady flow. It has to be a steady flow because they coincide, right? Okay.
A streak line is a little different. It is the instantaneous locus or trace of all the fluid elements that pass through a given fixed point in space.
So like right
If
there.
we run a short, uninsulated section of a bubble wire steadily, it shows us a streak line. In steady flow, each particle coming past the fixed point moves down the same path, and therefore the streak line is identical to the path line.
Right? So nothing new. We haven't learned anything. So let's look at flow visualization that is moving. My God, I'm going to kill you. Why do they make it so hard on me? Come on now. There we go. Okay, all right, hold on. Here we go.
Do you think that in this case, the streak line or the path line will be the same as the streamlines?
Question, do you think that?
Let's look at a path line.
Raise your hand if you think the streak line and the path lines will be the same. Raise your hand if you think the streamline and the streak lines will be the same. Raise your hand if you can't keep any of them straight. Okay, so let's take 2 seconds, write them down, right? Here we have a moving fluid, and we're going to make some predictions for science. Okay, this panel here is going to move this way, and then this way, and then this way, and then this way. And from the left, fluid is going to flow. I want you to write down what you think, if any of the 3 will be similar. Let's remember what they are. Streamline, instantaneous flow, path line, if you follow a parcel its whole life. Streak line, all of the pieces that will pass through that one. Yeah, let's imagine, I paused it right now, right? So this is by definition an instant in time. And let's pick this point right here. Or let's pick a point right here. Okay? So all of the fluid velocity is now to the right, but only right there. So I could see the streamlines for the entire flow would obviously be more complicated. But right now, there is a path that this particle will take. And the velocity here is to the right. Maybe later on, it does something else. Okay? You ready? Yeah, let's have a look.
And C. Here is a single marked element entering at a fixed time in the cycle of a plate. As before, we superpose its path line.
And what was path line again? Single particle's life. Okay. So this is now going to become a line. They're going to watch a single particle. Boom. Super obvious. Everyone knew that that would be the path line, right? Yeah. So this is the nice thing about visualization techniques. They can actually let you see the flow. I think that's a counterintuitive flow. Was that equal to the streamline at the beginning? No, of course not. Why? This is going to the right. So it was like that. Okay. Okay. Ready? Streamline, streak line, and path line. This is the path line. This is the location where that single parcel, that friend of ours named Bob, he's in a little barrel and he's going down Niagara Falls. This is his path. Okay? Okay.
Now compare the path line with a succession of instantaneous streak lines entering through the same point. None of
What the heck was that? What are streak lines again? Fixed point in space. So the places where it ends up later are different than where that one at a single time was, right? So this one was at a single time here, and it did this. But this is now fixed points in space and changing in time. Do any of these line up with that? No. Why? The answer is simple. I'm going to say it over and over and over. What? It's moving. The flow is moving. Okay? So these are complementary tools, but one does not tell you everything about the other. In fact, in an unsteady flow, you need all three. That's why we made all three. Because it's not an exercise designed to make you hate me, even though it feels like it. Does that make sense? Okay, so we'll notice here, every one of these particles that's coming out of this location, okay, follows this streamline. Oh, sorry, streak line. But the streak line itself is moving because the flow is unsteady and we're looking at through time. Does that make sense? A streamline itself is fixed in time. So we won't be able to see that from this video until we take stills of it and overlay them. Okay? We'll see that in a few seconds.
the instantaneous streak lines coincides with the path line. Here is a second element entering through the same point, but starting at a different time in the cycle of the plate. Notice that its path line crosses that of the first element almost at right angles, and it leaves around the other side of the plate.
You see that?
Now you see elements.
Did that make sense? So you can see in the streamline, right? You can see it lining up with different parts of this. At the streak line, sorry, the streak line lined up with different parts of the path line. But now if I just wait half a second, and this is in a different rotational position, this new path line forms a right angle to the other path line. Okay, no? Okay. So here's a parcel of fluid that we let go over here. The original one went this way, slowed down as the top of this paddle came towards it, and then pushed it down over the bottom of the paddle. If I wait just a fraction of a moment, okay, and I let go of another parcel, it doesn't follow that same path. Instead, it goes down, and then it also runs into that paddle on the bottom, moving back towards it, and it pushes it in the opposite direction. Whereas when I looked at the streak path, or the streak lines, they were fluctuating like this, right? This is showing all of the locations that parcels will go. And each of those individual, that's good, I like that sound. Each of those individual locations is being shown on the screen. It's in motion. Okay, now streamlines, and we'll see these in a few seconds. Okay.
Marked at both times in the cycle of the plate.
Okay, do you see it here? So this is the new path line. There's the original path line. Notice how repetitive.
If we superpose the path line of the second element and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either.
Right? Now here's the streak line. And even though it's similar, now notice.
Now let's see about the streamlines.
Follow the parcel along the stream.
In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here.
Yeah, okay, we're gonna do that one again, because that is, I think, one of the most important.
If we take a transparent.
Shut up, sir. Unbelievable. No, I like his voice, but he needs to know that I want to go backwards. Okay, so notice that we were very okay.
If we superpose the path line of the second element,
remember that you can watch one on the top and then one on the bottom,
and compare it with a set of streak lines through the same point, you can see that none of them coincide with the second path line either.
Okay, here's the streak line. Here's your object, right? And there it goes.
Now let's see about the streamlines.
That is the parcel you're following on the streak line.
In order to find the streamlines, we need the direction of the velocity at each point. We can find.
Yes. Yes. Okay, hold on. Yes, that was correct. YouTube on the. Okay. So we need to do streamlines really quickly. Don't leave. Don't get excited. Stay where you are. You're still learning. Why isn't this working? Oh my God. There we go. Oh my God, why won't it let me do this?
Moving fluids form complicated.
I'm gonna kill this thing. Wait. Don't worry. Do not worry. Do not cry. Young ones. Stop. Don't even think about leaving.
Lines.
Don't even think about it.
In order to find the streamlines, we need the direction of the velocity at each point. We can find this from combined time streak markers, such as you see here. If we take a transparency of one frame of the multiple time streak line.
Okay, so what is he saying here? We're gonna take pictures. We have here all these bubbles coming out, and the flow is unsteady. So at a single moment, if you look at all the bubbles, that doesn't tell you the flow, right? You have to look at short intervals, and then you assume where the flow is going, right? So right now, your eye might be like, well, that's the flow. Is that correct? No. Do not think that. Okay.
And overlay on it another transparency taken a few moments later. We can connect the endpoints of the streak lines and show the particle paths for short time intervals.
Okay. You see how the flow is different? All right, so we're going like this. Right? And these are the streamlines for a specific time.
Here you see the short dashes made by connecting the endpoints of the time streak lines. They show us the velocity direction at each point. If we draw lines parallel to them, these are the streamlines.
So
The total
slow.
streamline picture.
Okay, good. So here's the streamline. Okay. So I want to leave you with one thing and then you're allowed to go. What is special about these streamlines? What do they not do? They don't touch. They never touch. Fluid doesn't go into itself. That's not how flow works. We will talk about rotation and stresses and whatnot, but when you look at streamlines, streamlines are the same type of formalism that we'll use, and we'll talk about this again on Monday with E&M. Magnetic field lines don't cross. Electric field lines don't cross. Streamlines cross. They start and they stop. They pile up. And in fact, piling up will tell you something really cool. Okay? Questions? Watch that video if you want. It's only 35 minutes. It'll put you right to sleep.
That's like any 60 educational video.
I know, they're so good.
One part of it. And it's entire area that any part of it.
That's